So for today, we will go around the dual problems. Have you learned anything about dual problems before? Lagrangian. Lagrangian, you heard of the name?
Yeah, heard.
So who's that guy? Okay, you heard the term. All right, then. So yes, today we will consider the dual problem of support vector machines, specifically the training phase. And the reason that we have to do that is because there were some properties that we will get after we are deriving, or maybe after we have the dual form. And it just turned out that there are two important properties that really it changed the way that support vector machine used to work. Okay, for the first benefit, it is found out that before I go to that, first of all, if we use the primal problem to solve for, let's say, the parameters in support vector machine, namely there are normal vector, that was like a bias term that shift up and down. That was the sat term, that was like the slack variables that if this value is high, this means that it allows the incorrect points into training. Okay, just to recap. Okay, I'll just go over the previous day. Where was that? Okay, this is what we've learned last time. Like, this is a sat value. This is the normal hyperplane. Sorry, the normal vector to the hyperplane. Like this one. And B here is like, how would you shift this hyperplane up or down? Okay, but you also have like additional variables that was the sat variable. Sat J. Set J is like how far you want the incorrect point to go over. For each point, the value for that can be different. That's why you subscribe it as J. So that was the slack variables. And if we want to turn this soft margin SVM into some dual problem, it is possible. But if you want to do that, that means you have to consider these three variables as part of your problem. That is how we turn it. So when we turn a problem into a dual form, usually what it means is that you are still aiming for the same thing, but you actually did it in order to remove the constraint part. Because if you remember, if you have like a normal optimization problem where there's no constraint, you can do the differentiate and equate that to 0 and just find that value. Like, it was simple. But once you have constraint, usually this constraint will cause some discontinuity. For example, if your constraint was like around here, so it's kind of like your function is chopped up into pieces. Or maybe if your constraint make you to consider only this region. But the thing is, if we have so many constraints, like in this case, you have J constraints. This means that if you have 1,000 points, you have 1,000 constraints. That's why we want to solve this problem with like in its dual form instead of the original form. Because it is like that you are minimizing this equation, which looks very simple. It is like a quadratic and an affine. A quadratic in W and affine in sat, right? But the thing is, you have like 1,000 constraints if there were 1,000 points. That's kind of reason why you don't want to do it directly. That's why we want to turn it into some dual problem. Therefore, we can somehow shift these constraints out and put it as part of your objective function. Actually, that's kind of the whole entire reason why people would normally consider the dual form. That is because they don't want to deal with this kind of restriction. Okay. Well, that was like the main reason, but also, yes, as I mentioned before, there are two additional benefits after we turn an SVM into a dual form. The first benefit is the fact that, as you will find out, once you solve this maybe additional variable from the dual problem, you'll find that many of the solutions from this step will turn out to have zero value. And as it has zero value and you can plug that value in to compute the normal vector, you'll find that there's so many points that are going to have zero value. Therefore, computing this normal vector will only use a few data points. So efficiency was like the first benefit of turning this main problem, we call it primary problem, into the dual problem. The second benefit is the fact that once you have the dual problem, it just turned out that this term, this dot products between vector, would allow you to change it into some feature mapping function. So you have a different mapping function from linear. You can impose different mapping function. For example, as I showed before, like if you just consider a normal linear mapping, right? It will just be that, it will just be the original problem of SVM, which is just this simple mapping. In dual form, it kind of look like this, but in fact, you can change this mapping into other function. For example, you can replace that with some polynomial, which is like still dot products between vector, but you also have this like power term to kind of changing the mapping dimension. Also, you can replace that with some radial basis function, or you can change it to the hyperbolic tan function. Like all of these can be substituted into your dual, into this term in your dual form. So that is like kind of the reason, second reason why you probably want to turn your primal SVM into some dual problem. So yes, just for now, just kind of know that there are two reasons, but we will see how we turn this primal problem into the dual problem, and we will see how this can happen. All right. Okay. So first of all, I'm not sure if you can remember, but maybe I'll just recap a little bit about Lagrangian primal dual stuff. Okay. When we have a primal optimization problem, let's say this problem is a convex problem. Convex simply means that you are able to find the one global either minimum or maximum, but in this case we are focusing on minimization, therefore there's global optimization, global minimum point. Yes, that was the point that will give you the minimum value. That's convex. And with this, let's say convex function, if you plot it as a function of x, let's say if this is a function of fx, in this optimization problem, x is the variable that you are optimizing. How should I say? It's like the variable that you are varying such that you can optimize the value of your objective function. That is, if you change your x, fx could either go very low, but of course, since it's a convex, there will be like a minimum point for you, like a global one, like this one. And you can change x such that the value of function increase again. But of course, in this minimization problem, you want to find x that give the lowest value for fx, right? And if you plot the function of fx and x just like this into, like in this planner, you can see that, yeah, fx would just vary according to x. But what if you extend the dimension of this a little bit? from fx and x to maybe fx and another variable such as alpha, you may see that if you extend the dimension of this parabola on the dimension of alpha, you will still get the same parabola shape. But this time it's like a surface. But that surface will do nothing with alpha. It's like it's going to have a constant value across different alpha because it's not a function of alpha. But if you change x, then that is the only time where the value of fx would change because it's vary across x dimension. So this is like the first observation. In Lagrangian form of this optimization problem, this is when you actually move the constraint, in this case it's gx that you have, into your objective function. But you didn't move it just like normal move. You move it and multiply with some Lagrangian parameter alpha. So in this case, you can see that your alpha value is constrained to have value greater than 0. And if originally your constraint has a value of greater than 0, this means that you are having a convex function negate with some affine term. So if you think about this normal parabola value, if you negate it with, let's say, a function that was like this, then it's just like you shift this down and maybe you end up with a function that was like, like it probably changed the shape a little bit according to what was the term that you used in negating itself. In this case, I actually try to visualize what the consequence of negating with the gx might look like. It may not look exactly like this, but this is just to give some intuition of what it could happen. That is, originally, if alpha was 0, this means that it should, remain to be the same fx. But as you increase your alpha, this means that, also gx is greater than 0. This means that it will keep decreasing the value of your fx downward. It depends on how gx could affect your fx, right? So as you are having this as your main objective function, what is happening is that if you were to find x that will turn your Lagrangian into somewhat the same as your primal, this means that in order to find that, you should somewhat, as you are having this surface instead of the primal surface, this means that what you would do is that you probably have to tune for alpha somewhere on this surface. Maybe you are, like it could go anywhere, alpha. But of course, to find the x that give you minimum value, you still have to search for, it is like the value of fx along this surface. So what alpha could be? Alpha should be somewhere that is still somewhat slightly relaxing this surface to something close to the original problem, but it should not go as far as, go to like alpha leading to infinity, because if alpha is very high, this means you would lose the shape of fx already. You would turn everything into gx. But if your alpha is equal to 0, this means that you are now going back to the original fx. But as you know, you have to consider for the condition that gx can be true, but this time you turn it to Lagrangian. This means that alpha should have some small value such that it relaxes your primal objective function, but also enable your gx to keep its condition the same as the primal. On the other words, when you are turning the primal problem into a dual problem, it is like you relax your main objective function to include some terms in the condition parts of your optimization problem, and you relax that by scaling it with some alpha value. In order to find x, that is what you want to find to give like the minimum, to minimize this fx. It just turned out that when you change your objective function to be this one, like a Lagrangian term, you have alpha as another variable. So how to find x? That means you have to somewhat maximize your alpha. Sorry, maximize this objective function with respect to alpha. So it's seemingly like you are moving somewhere close to the original form of fx, right? But you don't know like which one. It could be alpha equal to 0 or alpha greater than 0, but should be somewhere small. And then you still have to compute the minimization of the Lagrangian objective function with respect to x. So it is like you still have to search for x that minimize the surface. So that's kind of like the meaning of turning from primal into dual. So yes, it is seemingly like you're adding another variable. But in order to consider this variable, you probably have to do something to make sure that when you tune this variable, it will somewhat causing your objective function to be close to your primal objective function. And you still have to perform minimization to find x that is satisfying and is suitable to your objective, that is to minimize. So that's the whole entire thing, geographically. But now we will look at them as a procedure. When we turn the primal problem into dual problem as a procedure, what you do is that firstly, you turn it into some Lagrangian form. And this is simple. Pretty much you move the objective function here and you move the constraint function here. And you multiply that constraint with some alpha. If you have one constraint, just one alpha. If you have more than one constraint, you have multiple alphas. All right. Then what you have to do in order to turn from Lagrangian into some dual problem is that, well, as you can see, the constraint for dual problem and Lagrangian remain the same. What is different is that you're now having to find the infimum of your Lagrangian cost function and perform maximization over alpha. So that is what you have to do. Then I believe many of you, or maybe some of you, will have this question. So what is the infimum of this Lagrangian function? Infimum pretty much means the lower bound. So that means that you have to find the lower bound of the Lagrangian objective function. And this is a lower bound with respect to the primal variable, that is x for in this case. But in our case, it will be the bias, the normal vector, and the slack variable. So how should we do it? How to find the lower bound? What we would do is that we will take the gradient. Okay, if in this case we have only one x, infimum of this will be equal to, if you were to plug in x, let's say we call it x hat, where x hat is causing the gradient of L, same function, equal to 0. So that's what you have to do. So x hat, or maybe whatever x that is providing you the lower bound, is the one that causes the gradient of that function equal to 0. So that's it. Okay. So let's go back to our original problem. The first step, as I mentioned before, we turn primal into Lagrangian by keeping the same cost function up here and move the constraint, whatever, down here. Here, as you can see, we have two constraints. two set of constraints. The first one, we will use alpha j to be like a Lagrangian parameters for the first set. The second set, we will use beta j. And once you have those two, you multiply beta j with the set j and alpha j with the first constraint, that is a constraint for mapping on the right side of the plane. And then you get this term and that term. So that's your Lagrangian. After you have the Lagrangian, what you need to do next is to find the infimum of the Lagrangian. In order to do that, as I mentioned before, we will find this infimum by finding the normal vector, the bias, and the slack variable that cause the gradient of that function equal to 0. Okay, so we will have to compute the gradient with respect to the normal vector, the gradient with respect to the bias, the gradient with respect to the slack variables, and equate them to 0. Okay, and the following we will do exactly that. Okay, firstly, this is our Lagrangian objective function, right? And secondly, these are the terms that comes from like a main primal objective function, and the rest of that are the term that we add from the constraint. What I did next was that then I grouped the term correspond to the normal vector together. For example, I put this term here together with up here, and then I move those terms correspond to the normal vector up here. And then for the bias variable, there's only one term correspond to bias variable. Meanwhile, for the slack variable, there are many terms. For example, there are this set j here, that set j there, and over there. So we put them together. We group them together so that we can now, take the derivative with respect to the corresponding variable. For example, if we take derivative with respect to the bias, we will only consider this one term. We take a gradient, equate that to 0. And as we equate it to 0, and because this is like an fi function with respect to b, so this means that the only way to cause this term to equal to 0, this means that it is a summation of alpha j and yj. Like this have to go to 0 so that it will be providing the infimum value with respect to b parameters. And likewise, you do the same thing for stat. Stat is still because the objective function is somewhat an fi function according to stat. So this means that if you take derivative of this and equate it to 0, you will get that, the only way to reach infimum is for this c, alpha, and beta equal to 0. So it's the same as previously. And finally, for the normal vector, we do the same method, that is, we adopt only these terms correspond to the normal vector, equate that to 0. But this time you will see that actually for this term to equal to 0, the normal vector w has to be equal to this term. It is this one that I wrote here. And after we know what is going to be, it is like what is the value of these variables that are causing the infimum. We know that actually for b and z here, they can have any value. But what causes 0 is actually, either the sum of alpha j, yj, or it is this c minus alpha j, beta j that is equal to 0. So it's like, for these two variables, they will reach infimum only if these are 0. These two conditions are 0. So that's actually, it is like the things that will cause infimum here. But meanwhile, for the normal vector W, what is causing infimum is that when W is equal to this term, and if you plug them in, you will get that actually the term corresponding to the W, if you replace that value back, it will be equal to minus 1/2 times the W square. So, yep, that's how it goes. So after you have like the value of the B and Z that is causing like the zero gradient, you plug it back into your Lagrangian function, just like what we say here. So we plug it back. So we know that for the first term, that is all the term correspond to the W is equal to minus 1/2 the W square. We just plug it back. For the second term at the infimum, actually this term is supposed to equal to 0 because we know that, you know, in order to cause infimum, this summation of alpha j, yj has to be 0. And lastly, for your set term, we know that, you know, c minus alpha j, beta j has to equal to 0. Therefore, the summation of this term will be equal to 0 at the infimum. So this means if you add them up, you will only have this minus 1/2 the W square plus summation of alpha j term. Actually, this alpha j term is like the only term that corresponds to this minus 1 here. It's like if you multiply alpha j back into this equation, you will get this alpha j. But it's like a standalone variable that does not tied with B, Z, or W. So when you find the infimum with respect to the primal problem variable, you will not touch this term. So that's the only term that was left. So that's kind of the reason why at the infimum point, this is an infimum value for your, it's in the infimum for your Lagrangian main objective problem. So this means once you have this, you can plug it back into your dual problem, which will turn into maybe something like this, that you can write this as, you know, like you can replace this entire term with this 1/2 the W square plus sum of alpha j. This is the infimum. Subject to alpha j, beta j greater than 0. This is like the condition that happened due to using the Lagrangian. But also you have other conditions that comes along the way. And those conditions are the condition when you derive for the infimum. That is, sum of alpha j, yj has to be equal to 0. And c minus alpha j, beta j equal to 0. So there are two additional. Okay, for OJ then. These are the two additional constraint that comes along the way. So what does this mean? It means that now if you want to solve for the W, what you have, you know, your normal vector or your bias vector, what you have to do is that you have to solve for beta and you have to solve for alpha and beta with this optimization problem, which if you look carefully, this means that actually this term are kind of, you know, like, okay, I cannot really cancel it because if you put the bill back into its, you know, like where it came from, it's actually alpha I, alpha j. So actually you have like a affine term of alpha. And you have some condition for beta. So this means that, I'm not sure, but I think this one is like a quadratic in affine, in alpha. So it's a quadratic in alpha. This means that yes, once you have alpha, you have to plug it back into this equation in order to get W, J, and also you have to use some constraint in order to go back and compute for B, which I cannot remember, but if I remember correctly, computing B will require like another, let's say if we have the view here, and if we know if we have the training data for Y and for X, and we have the view here, we can compute B back. So this is like how you would trace it back from your dual problem into the primal problems variable. Like the view and B and SAT are the primal problems variable. Okay, so sorry for a lot of math. But yes, everything can trace back. Thing is, actually, one may argue that, this sounds very much more confusing than if we were to solve just a primal problem directly. Okay, so let's see. Because it's actually quadratic, and that was like an affine term. This one is quadratic. It doesn't seem that different, right? And you also have some affine constraint, right? But the thing is, actually, once we come up with this dual problem, there are certain properties that we can get from it, and actually that will help us reduce the computation using dual problem. So let us first go back to the primal conditions. That is this condition where you have like the condition that will allow some slack variable, and also the conditions that you wish that most of the points will be mapped by the function into the correct place. And here we will analyze how is this and this conditions in the dual form are related, and that will lead to why we can reduce the complexity with the dual problem. Okay, but before we go, let us describe a little bit about this complementary slackness. Actually, complementary slackness are the conditions that will guarantee the value of the dual and primal to be the same. So what does that mean? Okay, let's just look at the primal and the Lagrangian. Actually, the dual and the the dual and Lagrangian, they are somewhat interrelated anyway, but let us look at these two, like a primal and Lagrangian. So firstly, if we look at the primal objective function, we have these two terms. In the Lagrangian, we have these two terms plus the rest. The complementary slackness is the condition in which it gives the value of this primal objective function to be the same as Lagrangian. So that means all of these terms have to be equal to 0. That is a complement. So the complementary slackness will be the condition in which these are 0. So this means that it is the condition where alpha j times this term, which is this, equal to 0, and the condition where beta j times stat j equal to 0. And in this case, I would like to provide some new notation. That is, let's define hj of p as the function of this, like the constraint of the primal. Not sure how to name it. There's so many names at the moment. Where p hat is actually like a set of the normal vector, bias, and slack variable. It is so that I don't need to write a very long sentences. So this means that the complementary slackness conditions are going to be alpha j times h of p hat j equal to 0, and beta j and set j equal to 0. That's the complementary slackness. It is the condition that makes Lagrangian go back to primal. And if we look at the graphical interpretation, actually, if this is like a Lagrangian, like a Lagrangian objective function, it is this one, right? It is just like the condition that caused this entire term to go 0. So this means that it goes back to the original fx that was just this curve, right? So that is the complementary slackness effect. Like if this go to 0, so definitely all the Lagrangian will go back to the primal problem. Okay, now the reason that we consider the complementary slackness is because we want to see the relationship between primal and dual, and then we will see the reason why as we turn this problem into dual form, why it actually saves our computation. And as I give a hint before, in the dual problem, we will see that actually a lot of alpha value will go to 0. We will see this fact with this analysis. So first of all, let us recap a little bit about SVM. There are points in SVM that are on the correct side. So that means this point will have set j equal to 0, right? No slack variable because it's mapped to the correct side. And yj times w transpose xj plus b will have value greater than 1, like strictly greater than 1 because it was mapped to the right side. Or on the other word, if we are turning this into like a h function, we can write this as like a h of p hat j equal to this, but it's greater than 0. Is everything all right? You saw me, okay? I'm sorry. It has a lot of math. I cannot help. It's just what it is. All right. So this is like a condition that you probably have to be satisfied. This is a condition that will be satisfied if points lie on the correct side. But if point lied exactly on the boundary, well, if it was the case, that j is still 0 because no incorrect map. But okay, this time your hj of p, or in the other word, which is equal to yj times wj transpose xj plus b here minus 1 will be equal to 0, right? And for the points that lies on the wrong side of okay, we're going to write this condition. These are the points where set j will be greater than 0. And hj of p will be equal to yj times w transpose xj plus b negate 1 plus set j equal to 0. So as we have these three, let's say, situations that we will normally find in the primal problem, we will analyze them together with complementary slackness, and we will see why we may get most of the alpha j equal to 0 in just a moment. Okay, firstly, if all the points lie on the correct side, as I mentioned before, we get the HP greater than 0, we get set j equal to 0. If we want to satisfy the complementary slackness, this means that for alpha j HP to equal to 0, we need alpha j to be equal to 0. Meanwhile, beta j does not necessarily equal to 0, it could be greater than 0. And if we plug that in to the dual condition, we'll see that because alpha j equal to 0, this means that beta j will have to be equal to c. And this is what you would get in the dual condition when points are mapped correctly. And if we are using SVM, that means most of our training points will be mapped correctly. This is when your alpha j will have its value equal to 0. And when alpha j equal to 0, what it means is that when you compute the normal vector W with this formula, this formula, if alpha j equal to 0, this means that you can skip so many terms, right? You don't need to go all over, let's say, every j term, and actually j here denoting the indexes for your training samples. So if you have 1,000 points, and let's say 900 of them are mapped correctly, this means that you only need 100 points to compute for your normal vector. And that 100 points are definitely not the points that are mapped correctly, but it's going to be the points that are on the support lines or the points that are incorrectly mapped. So yes, we have the other two cases left. So here is what it looks like if the points lie on the supports. Okay, when the point lie on the support, that is when your head j equal to 0 and set j is equal to 0. So that means your alpha and beta does not need to have 0 value. So that means that it has certain value, but is still somewhat restricted by C parameter. And don't forget that C parameters is the parameters in your primal. It's actually the one that you use to control whether or not you want to allow a lot of slackness in your primal problem. So large, if I remember correctly, if your C is large, that means you are allowing so many incorrect map. If your C is small, you're not allowing a lot of incorrect map. But we will have to go over that again, I believe. Anyway, that's your C parameters. So actually your alpha and beta, for the case that there are points on the support, the value for alpha and beta is going to be somewhere between 0 and C. On the other hand, if these points are incorrectly mapped, that is yj times w transpose xj plus b will be equal to 1 minus zj, and zj will be greater than 0. So this means that your hj will still be equal to 0. That means alpha j can have any value that is not 0. And if zj is larger than 0, this means definitely your beta j has to be 0. So this means that is, for the points that are incorrectly mapped or mapped on the wrong side, they are actually those points that correspond to where your alpha value will definitely has a value equal to C. And C is the parameters that control your slackness. So if you put this together, this is what you get. But this time I kind of put a dual here on the left-hand side and the primal on the right-hand side. You can see that whatever I said previously actually came from this end to this end, but now I kind of sweep the location a little bit. It is because the reason that I can sweep it like that is because we have this complementary slackness that we satisfy. So this means either it's dual or primal, they should reach to the same conclusion or maybe same objective function. So in this case, this is what you get. As we can see here, the case where you correct map, your alpha j equal to 0, this means those points aren't going to be the point that contribute to computing your normal vector, but actually those points that are on the margin or on the supports and on the wrong side of the supports are actually going to be the point that is used to compute your normal vector. So this, to just summarize it again, actually I wrote it here as well. As we know that, if we derive this relationship that W will be equal to the sum of alpha j, yj, xj, and that came from when we find the infimum. It's actually another constraint, but I didn't write it down because it's more like substituting with the value. Yeah. So yes, you probably get alpha from these two cases and use them to compute for your normal vector. So that's how it's done. And since normally if we can do SVM classification, that means most of the points will be correctly mapped. So this means that, as I mentioned before, if we have 1,000 points in our training, 900 of them are going to be correct map. That means you only need 100 samples to help you compute alpha j. And then once you have the alpha j, you can plug in to this formulation to get the normal vector. So that is how the dual and primal problems are related. Okay, so in these slides, I just do some summary of all the conditions that we've seen before. For the first one, the first types of the condition that we've seen before are the primal feasibility, or the, like the condition in the primal problems, right? The second types of the condition that we've seen are actually the first derivative test. That is when you take gradient and equate the objective to 0, right? And then the other types of the condition that we've seen are the complementary slackness. That is the condition where you ensure that your dual and primal are having the same value. And finally, you get a dual constraint. That is the dual, the condition where you would have it if you were to solve the dual problem. So that's it. Like all the types of constraint that we are dealing with this situation that we want to turn the primal SVM into a dual form. All right. There's a little side note. I'm not sure if you have this kind of questions, but I had when I tried to prepare myself for this lecture. That is, when we talk about complementary slackness, we will usually, it is like we know it is condition where, let's say, alpha j times hj equal to 0. And when beta stat j and stat j times together equal to 0. And we normally consider the case where if one is 0, the other would not be 0. And I have a little questions like why? What's going to happen if both values are equal to 0? If both stat j and beta j equal to 0, simply it means that actually in your primal problem there's that constraint for stat j does not exist. Or what I wrote it here is that let's say if alpha j times hj equal to 0, usually what we would consider is when alpha j or hj equal to 0, but not both equal to 0. Otherwise, it just means that constraint doesn't exist. So this is something to keep in mind when you analyze, because I understand that for some students, when they go back and try to recap, they will somewhat have this idea then when both are equal to 0, why we just consider one, not both, one of them. Okay, so hopefully this proved to you the efficiency if we were to use dual problem in solving for the SVM hyperplane. Another benefit of using the dual problem is the fact that we can impose some kernel mapping, or on the other word, sometimes I normally use this kernel mapping as if it was like a function mapping, but we will see why I kind of consider those in that way. So as we can see, if we look at the dual problems, we will see that there are terms where x transpose xj exists, and that one as well. Be careful for the one up here, xj and xi are both training. And the one below here, your xj prime is training, but your x here will be testing. Just need to be careful when you use the formulation. And or you can rewrite it as, like W transpose X in your inference. But the thing is, as you consistently having this kind of dot product terms, some people start to have a question of whether or not we can replace this dot product term with some kernel mapping. So you can think of kernel, like a simple kernel mapping is like when you perform the dot product between two vectors. So the one that you see immediately from the linear SVM is this linear kernel. But actually there are more than just linear kernel. Like in this example, you can replace those dot product term with some other function like the polynomial that is like a linear with the polynomial order. With this higher order. Or you can replace it with a radial basis function, and you can also replace it with the hyperbolic tan function. But the thing is, actually, not every function can be used as a kernel function, and we will see a little bit of the condition for the kernel function, but that will be just a little touch of what this kernel function could be and why it's there. Okay, firstly, let's consider the fact that when we use SVM, right, we have X, J, that is going to be our input feature, and we normally have it with YJ. That was the target ground truth, and we probably consider, all the J from 1 up until M, and if there was 1,000 samples, then M would be equal to 1,000 for your training set. Thing is, you can do whatever with X before, using it for training for SVM. So X is your input features. You can map it with whatever way you like. You can use neural network, extract the hidden features, or you can use some function to turn this feature into some higher dimension feature. But whatever it is, at the end, when you plug it in to this dual problem, you will see that at the end, all you did was to compute the dot products between them. So that is like the reason why actually you can choose two ways. First way is that you pre-compute xj into some higher dimension feature and plug it into SVM. Or you can use some function to turn this xj into something else. For example, if you would just plug in the normal xj into the kernel function, of course your kernel function can somewhat extend the meaning of this xj into something else. Like for example, if you are having the feature that are, like having this donut boundary like that, your kernel function could map some of its points up here, and then you can easily perform the hyperplane cutting. And if you do this, you need to guess whether or not your input features is going to be useful, right? Because if you do it this way, simply mean you are enabling SVM to find the best features and the best cutting in itself. But of course, yes, as the theory suggests, you can also turn X into something else and plug it into SVM. Because all it needs is that, like it just received your X here. It's like a dot product term. You can replace it with something else. So that is like kind of the reason why we are considering different kernel function, because we see that actually, you don't need to preprocess X if you don't know what features that X could be. That would be informative for SVM. On the other hand, you can just use a kernel function that is most suitable for your data distribution. And that can also return you some feature mapping and also provide the better mapping function for your SVM to work on. So that's the benefit of your kernel function. And the thing is, what are the functions that you can use as a kernel? Okay, immediately there are two conditions for these types of function. Firstly, it has to be greater or equal to 0. Just like if you think of the X transpose X, Xi transpose Xj, this is like a correlation mapping or maybe covariance mapping. So pretty much this function, if you do this, this is like greater than or equal to 0. And also, it has to be somewhat symmetrical. So this means that the order of Xj and Xi can be switched. And there's no differences between them. So yes, the following are the example of what kernel function could be. Like you can use many types, and the very simplest one, that is the linear one, is just the normal Xj transpose Xi, something like that. So it's just the normal dot products between two vectors. And I think that's it. So, yes, because you've seen the example of these. Like you have, like by default, you have Xj transpose Xi as this one. You can replace that with some polynomial function or radial basis function. Thing is, if you notice carefully, like for the polynomial, you have two additional hyperparameters. And for radial basis function, you have this gamma parameters. For this hyperbolic tan, you have this gamma and beta parameters. These are hyperparameters that it is like you need to find them. But since they are hyperparameters, you can find them by perform the validation or cross-validation if you don't have a lot of data points. So it's pure data driven in a sense that it is like for your kernel mapping, which is usually being like a fixed procedure where people could do some feature extraction and put Xj on use with SVM, or you can choose to somewhat train for the hyperparameters using validation when you are learning for SVM. You can do it both ways, but what happened around, I'm not sure, but it's like before neural network or deep learning, usually people would consider SVM as a very powerful tool because it can learn the underlying value for these hyperparameters that would well describe the feature mapping. And will make it kind of makes sense in a sense that whatever feature mapping that you did will correspond to how you would cut your hyperplane, because it just goes together as a function in your dual form, like here. So it is like all together as once. End-to-end training, sometimes people call it that way. So that's why it used to be very powerful. And if I remember correctly, SVM was like an graphical model, like another tool. These two are actually the very powerful tool before deep learning became famous around year 2016. Yep, that's it for today. And for the rest of these are just example as to how you can tune the hyperparameters and what it might look like. And as you can see here, whatever shape your data distribution was, radial basis function happened to be the one that gives you probably the best possible mapping, because it's quite, how should I say, it's quite flexible in terms of the function. But of course, polynomial is another, it is like another kernel that people normally use as well. Yes, in here I just provide some example of what it would look like if you maybe increase C value for your slackness, for the slackness in the SVM problem, and what it would look like if you would to increase the gamma value for the radial basis function, what it would look like. So yes, that yeah, you can look at this example. This one I kind of try to tune for the C value. Yeah, this one is just varying C. This one is varying the gamma value in the radial basis function. Just as an example. Yeah, that's it for today. We can